morning, dear students. Welcome to this session on pre-stressed concrete. We are calculating the uh, total losses in the pre-stressed concrete members, both pre-tension and post-tension. So these are the things which we discussed in the last few sessions, and the very last session also we have calculated the total losses in pre-tension members, especially. Uh, there are four types of stresses, losses in pre-tension members. One is elastic deformation, uh, creep of concrete, shrinkage, and relaxation of steel. So there won't be any frictional loss, and there won't be any anchorage slip. So those two will be absent in this case, right? And now let us, this is what happened in the last session. Till the last session, we have seen these examples. Now let us talk about this example. A pre-stressed concrete beam, 200 mm wide, 300 mm deep, is pre-stressed with wires having area 320 mm square. Okay? Located at a constant eccentricity of 50 mm, carrying an initial stress of 1000 Newton per mm square. The span is 10 meters. Uh, so what we understand that the beam is having constant eccentric tendons. So, for example, if this is the CG of concrete in centroid location, neutral axis other way. So 50 mm is the constant eccentricity of the tendons. So this value is TMM. Okay, right. The problem doesn't say there are so many wires. It only gives you only the cross-sectional area of the tendons. It is not like number of wires with a particular diameter. Okay, that also be the option. So in this case, you are being given there are some number of wires with some dia. You are being given with cross-sectional area. The span is 10 meters. So span 10 meters. Calculate the percentage of loss of stress in wires for both the cases. If treating the beam as pre-tension and also treating the beam as post-tension, and use the following data. Young's modulus of steel 210 kilonewton per mm square. Young's modulus of concrete 35 kilonewton per mm square. Relaxation of steel 5% of the initial stress, and shrinkage strain for pre-tensioning 310 power minus 6. These are all standard values. If at all, if any data is missing, you can assume always this data. Pre-tensioning, I mean shrinkage strain, epsilon sh value, okay, 210 power minus 6 for post-tensioning. Creep coefficient phi value is 1.6. Slip in anchorage, that means delta value is 1 mm. Okay, and frictional coefficient for wave effect, I mean constant k value given. Mu is not given, so leave it. Only we use k value. Okay, for wave effect. Okay, right. Now let us proceed for the solution. So you have stress value. Okay, you have area. So stress into cross-sectional area is giving you force, pre-stressing force divided by 1000 into kilonewtons. This is newtons, 320 into 1000 newtons divided by 1000 kilonewtons. And cross-sectional area of concrete, 200 into 300, that is this value, 6 into 10 power 4 mm square. Okay. Then modular ratio, you know the formula, Young's modulus of steel divided by Young's modulus of concrete. These two values, 210 divided by 35 is 6. Moment of inertia, whatever are needed for the solution, you are calculating prior to that. So B h cube or d cube by 12, 45 into 10 power 7 mm power 4. Right, now getting the stress value in concrete at the level of steel. Okay, so we know the formula, it is like P by A plus P into E into, this is like M by I into Y, your bending stress. This is M value. Okay, so that is what is done here. Capital P means pre-stressing force just calculated, 320 kilonewton. Convert into newtons divided by cross-sectional area of concrete. P into eccentricity 50 mm divided by I value just calculated, and Y means location of steel from centroid, I mean neutral axis, is 50 only, same. Right, this is stress value 7 Newton per mm square. Right, now calculate the loss of stresses. So just made a tabular form, pre-tension beam, post-tension beam. Right, so first loss to be calculated, elastic deformation of concrete. And you know the formula, it is like modular ratio into stress. Okay, I mean alpha E into Fc. So what is modular ratio? 6. What is stress value? 7. So total loss is 42 because of elastic deformation. Okay, and there won't be any loss if you treat that as post-tension beam when all the tendons are stressed at a time. So there is no information in the question that there are so many cables and the cables are tensioned one after the other successively, not simultaneously. There is no such information. So what we are doing, we are assuming that all the wires are tensioned at a time simultaneously. So uh, the loss of pre-stress due to elastic deformation or elastic shortening is zero in case of post-tensioning beam. Okay, right. Relaxation loss is same for whether it is pre-tension or post-tension. 5% of 1000. It's like 5 into 1000 by 100, 50. For both the cases, it is same. Then loss due to creep of concrete is same for both. Creep coefficient phi and stress at the level of steel and also modular ratio alpha E. Okay, same for both. Phi is 1.6 given, I mean creep coefficient. Remember there are two methods when you are finding loss due to creep. One is creep coefficient method, other one is creep strain method, ultimate creep strain method. Okay, depending on the given data, we use that method. So 67.2 is the loss Newton per mm square for both. Pretension and post-tension. It is will be there in pretension and post-tension. Okay. Coming to the fourth one, all three those of those are being copied again here, just to put it in a single slide. Now coming to fourth one, shrinkage. Shrinkage values of strains, shrinkage strain is different for different cases. Pre-tension it is higher, post-tension it is little lower value. It is 310 power minus 6, 210 power minus 6. So 300 into 10 power minus 6 means strain value into Young's modulus will give you stress value. Okay? Strain into Young's modulus. So for pretension, use 300 into 10 power minus 6. For post-tension, use 200 into 10 power minus 6. Just simply multiply this shrinkage strain SH with Young's modulus of steel. Okay, so this will give you shrinkage loss. Okay, right? So 21 here and 63 here. Now slip in anchorage or anchorage slip loss will not be there for pretension. Remember 0. Okay. It is only for post tension. The formula you know that it is E times delta divided by L. So Young's modulus of steel, okay, delta 1 mm, delta 1 mm given data. So delta 1 mm divided by, this is like slash, not 1, correct this one, slash, by L 10 meters, convert that into mm, 1000. So that is coming out to be 21. And frictional loss, same. Pre-tensioning member, there won't be any friction loss, 0. Only for post-tensioning, you know the formula, P naught into mu alpha, like P naught loss value is P naught into mu times alpha plus kx. Okay. Anyhow, whether it is no friction coefficient is given or not, or else even if the friction coefficient is not given, you can assume something like 0 0.5, 0 0.30, or you take it from the code, IS code. As the cable is straight, having constant eccentricity, slope is 0, alpha is 0. Okay, so that's why the first part of the equation is 0. This is 0. Alpha is 0. Angle between the tangents. Okay, take any 2 points on the tendon. The angle between those two tendons is alpha. So as the tendon is straight, there is no angle difference between the tangents. Okay, tangents are also going through the tendon. So only k into x into p naught. So p naught is 1000, k, x is 10 meters. You have to substitute that in meters because k value is per meter. Okay, 0.0015 per meter. So remember always that this shall be in meters, x value, I mean length of the beam. X means it is, we are taking total length L, so that it's 10 meters. Now that is coming out to be is equal to 15 Newton per mm square. Okay. So total losses working out to be, for pretension member it is 222.2. If you want it in terms of percentage, divided by initial stress is 1000. This divided by 1000 into 100 will give you 22.2%. And for post tension member, it is working out to be 195.2 Newton per mm square is the loss value. And if you want percentage, just divide by 1000 into 100. Okay, that is giving you 19.52%. Okay, so this is how we work out the total losses in the beam, both pre-tension and post-tension beams if you want. So just to note it here, for post-tension beam, loss due to elastic shortening will not be there if all the tendons are tensioned simultaneously. And for a pre-tension beam, there won't be any anchorage loss because there is no anchorage at all in pre-tension beam. And there is no frictional loss because there is no friction between concrete and steel. Okay, so these are the things to be taken care of. There are some typographical errors in the textbook that you have to be careful with that. Just don't follow whatever is there. Just like this, you have a divided by here, not the vertical line. Okay, got it. So this is one such example, right? Okay, rest of the problems we will see in the next session.